What's common in smartphones, computers, and your lightings? They all run on electricity, which means they all have electric circuits. But what are they? What are they made of? So let's understand the basics of this in this video. So think of electric circuit as paths, one or more paths along which charges can flow, one or more paths in which we can have currents. And this is a typical circuit that you might build in a lab. And every electric circuit has some circuit elements. Just like the elements of the periodic table are building blocks of matter, the circuit elements are the building blocks of electric circuits. So let's look at a few of them. The first circuit element is the voltage source. And as the name suggests, it produces a voltage or electric potential difference between any 2 points in the circuit. A common voltage source is a battery, which uses chemical energy to produce voltage, but other voltage sources like generators can use mechanical energy to produce voltage. But for our purposes, let's just stick to batteries. And the circuit symbol for battery is usually this. The long stick represents the positive terminal and the smaller stick represents the negative terminal. Now, technically, this represents a single cell. So if you have multiple cells in our circuit, we usually tend to represent them by drawing multiple cells stacked like this. But we don't have to worry about that. We'll just represent a single cell. That will be good enough for us. Okay, another circuit element is wires, which act like conducting paths, usually made of copper, but any conductor will work. Then we have resistors. As the name suggests, these resist or impede the flow of charges. You may be wondering, why do we want to do that? Wouldn't that just reduce current in the circuit? Yes, because that's necessary to limit the current. We don't want just any current in our circuit. We want to be able to limit it to exactly how much we want, and resistors are great at doing that. The circuit symbol for resistor looks like this. We just draw zigzag lines to represent them. Now, another technical note is that even your batteries and wires have resistance in them, but we often ignore them because their resistance values is usually much smaller than the resistance of the resistors that we add in the circuit. And so we call our batteries and wires ideal batteries or ideal wires, meaning we assume that they have no resistances. Then we have light bulbs. We want the current to do something meaningful, right? And so sometimes we want it to light up a bulb. So we have light bulbs, and the circuit symbol for light bulbs look like this. Now, again, a small technical note, this is the circuit symbol for the incandescent light bulb, the one that you're seeing over here. But a lot of circuits use light bulbs that look like this. They're not technically bulbs. They are called LEDs, light emitting diodes. They are usually more efficient, they tend to last longer, and they have a different circuit symbol. It looks like this. The triangle represents a diode. Diodes, their specialty is that they only allow the current to pass through in one direction. And this triangle represents which direction that is. So in this particular case, it only allows the current to the right. That's why the triangle is drawn pointed to the right. And these arrows coming out represent that it emits light. Anyways, and the final circuit element that we'll be concerned with is the switch. Just like switches at our homes, they are used to turn on or turn off the circuit. And if you're wondering how does one work, well, you can have different mechanisms. Here's the simplest one. Notice right now that there is a gap between these 2 points over here, which means this part of the wire is not in contact with this wire. And so the switch is open. So the circuit is turned off. What happens when we close the switch? Look, they come in contact and now they can conduct. And so we now say the switch is closed, the circuit can turn on, and charges can flow. So the circuit symbol for the switch is going to look somewhat like this. This is the open state, turned off, and this is the closed state, turned on. Now that we have the circuit symbols, this is what the model of that circuit looks like. So we can start analyzing our circuits now, but this looks pretty complicated. So let's start with the simplest circuit we can think of, just a battery and a switch. What happens if we close it? Will there be a current? Well, these 2 points are not in electrical contact. There is air in between, and air is an excellent insulator. It doesn't allow the charges to flow, which means charges cannot flow anywhere, and therefore there will be no current in this circuit. And so this circuit is called an open circuit because it's literally open. For a current to run, we want a closed conducting path. Okay, how can we confirm that there is no current? Well, we can use a device called an ammeter. If you connect that ammeter anywhere in the circuit, it will read 0. All right, there's no current in the circuit, but what about voltage? Oh, we need to be careful around that. So if the battery was, say, 5 volts, what does it mean? Well, remember, volts is a measure of joules per coulomb. So this says that if I go from here to here, the electric potential energy increases by 5 joules per coulomb. In other words, if the electric potential at this point was 0, then the electric potential at this point would be 5 joules per coulomb, which is 5 volts. And so the potential difference, that is the voltage, that is 5 volts. So there is a 5 volt of potential difference between these 2 points. But what about the electric potential at this point or this point? Well, think about it this way. If I go from here to here, will the electric potential change? Well, no, because there is no battery in between. And of course, over here, there's no current running. But even if there was current running, then remember, our wires, we assume them to be ideal, no resistances, meaning the charges will not lose any energy. And even ammeters have very low resistances, which means if there was a current, even charges moving through an ammeter, they will not lose any energy, which means the electric potential over here or here would be the same, 5 volt. And the same would be the electric potential over here. Similarly, electric potential here is 0, which means electric potential everywhere along the wire is also 0. So remember, even if there is current running in the circuit, electric potential along a wire or moving through an ammeter does not change because they have negligible resistance, and so charges will not lose any energy. And to measure voltage, we can connect something called a voltmeter. If you connect them across these 2 points, the voltmeter will read 5 volts. So a quick question for you. What do you think would a voltmeter read when connected across these 2 points? Why don't you pause the video and think about this? Well, since this switch is closed, the electric potential at both points is 5 volts. But what's the potential difference? That's what voltage is. The potential difference is 0. So this voltmeter will read 0. But wait, before connecting the voltmeter, this circuit was open. But now, isn't it closed? No, because voltmeters have very high resistance. So connecting a voltmeter across these 2 points is kind of like having air in between those 2 points. It does not close the circuit. So remember, voltmeters are connected across 2 points to measure the voltage. They have very high resistance. That's why they don't affect the circuit. And ammeters are connected in the circuit this way, and they have very low resistance, so they too do not affect the circuit. All right, but this was an open circuit with no current. How do I get a current in my circuit? Well, let's connect these 2 points. What would happen if we were to directly connect it with another wire? Now we have a closed conducting path, and so there will be current in the circuit. Okay, another important technical note, electrons will always go from the negative terminal of the battery to the positive terminal of the battery. But according to our convention, the direction of the current is in the opposite direction of the electron flow, and that's why it's in this direction. The convention has something to do with the history. We'll not get into that, but just remember that the conventional direction of the current is from the positive terminal of the battery to the negative. But anyways, notice that there is absolutely no resistance in the circuit, nothing to impede the flow of charges, which means the current in the circuit is going to be infinitely high. Now, of course, in reality, batteries and wires do have some resistance, and so the current won't be infinitely high, but it will be very high. And so this situation is called a short circuit. A short circuit is when you have no resistance or very minimal resistance, causing very high currents. And that is bad because high currents can damage the circuit. The wires can get too hot. If you had an ammeter over here, it would be maxed out and it would even get damaged, or its fuse can blow. Which means we're looking at 2 extremes over here, an open circuit with no current and a short circuit with infinite current. We want something in between. How do we get that? Well, we connect these 2 ends with some resistance. So let's do that. Let's connect them with some resistor in between. Now, there will be some current running. It would not be infinite. It will be finite because the resistor will impede the flow of charges. Just for the sake of some numbers, let's assume that current is, say, 0.2 amps. Again, notice as I go from here to here, the potential does not change because charges do not lose any energy because there's no resistance along the wire or even inside this ammeter. However, what happens when I go from here to here? Well, notice at this point, the potential is 5 volt. At this point, the potential is 0, which means over here, the potential is 0, which means when I go from here to here, the potential drops, the potential reduces. Again, you can measure that drop in potential by attaching a voltmeter. But what happens to that potential energy when I go from here to here? Well, that potential energy is converted into thermal energy. Remember, resistors impede the flow of charges? That turns potential energy to thermal energy that heats up the resistor. And now this energy can be used to do meaningful things. For example, this energy can light up a bulb. It can be used to cook our food. This is how we make electric circuits do useful things for us. So long story short, electric circuits are basically paths along which charges can flow, paths along which electric current can be established. Voltage sources establish electric potential difference between 2 points in a circuit, and resistors can impede the flow of charges. And when you have a closed circuit, our convention for the current is always from the positive terminal to the negative terminal. And because we assume that the wires are ideal, they have no resistances, the potential along a wire stays the same because charges will not lose potential energy. And ammeters have very low resistances, so even when charges move through ammeters, they will not lose any potential energy. And voltmeters have very high resistances, and that's why when you connect voltmeters across any 2 points, it does not affect the circuit because you have a very high resistance, kind of like air over here. And finally, when charges move through a resistor, look, there will always be a potential drop across that resistor, meaning the potential energy reduces and that gets converted to thermal energy, and that heats up your resistor.